In 1927, Albert Einstein boarded a train to Solvay in Belgium. His journey would take him to the center of an argument between the greatest collection of scientists assembled this century. By the end of this conference, Einstein had lost a battle, and our understanding of the world had changed forever.
Quantum mechanics, in a nutshell, is the physics of the very small. Anything as small as an atom or smaller than that works in accordance with the rules of quantum physics.
And it's a very surprising discovery that the physical world at that scale is totally different in its behavior and character from the physical world of every day that we experience directly. The everyday world is clear and reliable. The quantum world, it turns out, is cloudy and fitful. So that was a big surprise.
Quantum physics has revolutionized our understanding of the world. The journey to the mysterious heart of the atom has forced scientists to take sides in a debate about the uncertain nature of matter, a debate that still continues today. It all began in 1897 when J.J. Thomson discovered that electricity was caused by the flow of tiny particles called electrons.
What Thomson decided was that he had found a subatomic particle which is a constituent of all matter.
And why is that important? Well, our entire understanding of matter today, normal, ordinary, garden variety matter, why grass is green, why the sky is blue, that understanding is based on how electrons interact inside of atoms.
Although Thomson and his colleagues understood the scientific importance of the electron, they didn't see any practical use for it.
Could anything at first sight seem more impractical than a body which is so small that its mass is an insignificant fraction of the mass of an atom of hydrogen?
They in fact had a toast at one of their annual dinners, which was, to the electron, may it be of no use whatsoever. Now, that's obviously very ironic because the understanding of the electron has led on to tremendous practical applications.
This pulling of electrons from atoms isn't done for amusement.
The electron particle was to make its first commercial impact in the cutthroat world of the American telephone industry. In 1907, the telephone was already 31 years old. AT&T, the company founded by Alexander Graham Bell, was facing stiff competition from thousands of smaller companies. The race was on to be the first operator to provide a long-distance service between the east and west coast of America.
The technology to do that didn't exist.
Can you recall the telephone of a generation ago? New York to Denver was the longest call that could be made.
The major technological problem that stood in the way of completing a long-distance line was amplification. As an electrical signal travels down a copper wire, it weakens if there's resistance in the copper wire. Eventually it weakens to the point where there's no longer a usable signal. They needed a way to amplify the signal.
Desperate for a solution, AT&T invited anyone with an idea to contact them.
One person who did was an independent inventor named Lee DeForest. DeForest in 1906 had invented something called the Audion, the first three-element vacuum tube. He was using it primarily as a detector of radio waves, but he knew also that his device would provide a small amount of amplification.
But not nearly enough for AT&T. The Audion amplified the telephone signal by altering the flow of electricity between a metal plate and a wire surrounded by a vacuum. The problem was there was only a partial vacuum inside the Audion.
The space between the wire and plate is jam-packed with gyrating air atoms. And to reach the plate, the electrons would have to bump their way through them like midgets in a subway crowd.
The solution was to pump out more air. By doing this, the first useful electrical amplifier was born. AT&T used these high vacuum tubes to complete the transcontinental telephone line in 1914.
How much is your voice amplified by these repeater stations between New York and San Francisco? You say it. I can't. The figure is 10 with 99 zeros after it.
It was only made possible because of J.J. Thomson's earlier discovery that electricity was the flow of tiny particles, electrons. Theoretical physics had a commercial value after all. A lesson not lost on AT&T.
The transcontinental telephone line was an important step in knitting the nation together. The other effect it had was to firmly convince leadership at AT&T that bringing science in-house, hiring scientists, engaging them in doing research, was something that was a good business strategy.
They set up the Bell Telephone Laboratory. The high vacuum tube, or valve, became the workhorse of a new communications industry. Commercial radio and later television were made possible by the valve amplifier.
Yes, sir. If it weren't for these babies, there wouldn't be any radio.
At the same time, scientists were wrestling with radical new ideas about how electrons behaved.
At the end of the 19th century, it looked as though, essentially, we knew how the physical world behaved. There were the triumphs of Newton, which described how particles behaved, and gave you means of calculating what they would do. And then, in the 19th century itself, the great achievement was Clerk-Maxwell's theory of electromagnetism. That showed that light was a wave-like thing, waves of electromagnetic energy. And really these issues seemed to be settled, and many great physicists thought all that was left was just to tidy up the details, to dot the I's and cross the T's.
In the Victorian era, it seemed everything in the physical world was either a lumpy particle, like an electron, or a spread-out wave, like light. But in 1900, German physicist Max Planck saw there was a big problem with the wave theory of light. Planck was looking at the way light and heat radiates from hot bodies, like a furnace. Everything known about physics said that the radiation should behave like a smooth, continuous flow, a wave. But the calculations done with the wave theory didn't match observation.
Planck began to think about it, and he saw that you could get round this. The calculations were wrong because they were assuming that the radiation was behaving just like smooth flow, like the flow of water from a tap. He saw that, in fact, the radiation was not behaving that way. It was coming in drips, as you might say, in packets, one at a time. One packet of energy followed by another packet of energy. These packets consisted of so much energy, and so it was a quantum of energy, so much of energy, and that's where the name quantum and quantum theory comes from.
Planck's quantum theory suggested the seemingly impossible. Light could be both a wave and a particle. It was so impossible that Planck stopped short of saying so.
He found that you could only explain the way light comes out of atoms, the spectrum of light, in terms of little packets of energy coming out. But he never suggested that the light only existed as little packets of energy. And the analogy I like to use is with a cash dispenser at a bank. If you go to the cash dispenser at my bank, you can get money out in multiples of £5, but there's no way you can get £4 out because it can't give you coins, it can only give you notes.
The leap of imagination came from a young patent clerk who in 1905 dared to think the unthinkable.
Einstein said, it's the light itself that only exists in lumps of a certain size.
Einstein reinforced the concept that light had a particle character. The whole of 19th century physics has shown that it had a wave-like character, so the physicists of the day were left with this intolerable paradox, really, that sometimes light looked like waves, sometimes like particles. And I think it's fair to say that most of them were so upset by this, they swept it under the carpet and said, we won't bother about that. But of course some people persisted, and through their persistence, modern quantum theory eventually was discovered.
The revolution in physics would have to wait for more urgent matters to be resolved. By the end of the Great War, a new generation was now ready to question the established order. Physics was no exception. The catalyst for change was a young French aristocrat, Prince Louis de Broglie.
Louis de Broglie was a young student in Paris, and he said, OK, light has been found to have this funny behaviour. We thought it was waves, but it turns out sometimes it's also particles. Now, there are lots of things around which we've always thought of as being particles, things like electrons and so on, maybe they sometimes behave like waves. Maybe what's sauce for the goose is sauce for the gander.
We think we understand particles. We think we know what things like billiard balls are. And when you say no, you have to think of these things as being wavy as well as being particle-like. You have to apply quantum rules to electrons. That was a really big step.
De Broglie came up with the remarkable idea that everything is a little bit wavy while he was still a student. The theory gave his tutors something of a headache.
De Broglie's examiners at the university were reluctant to give him a degree for such a fool idea. He got the degree, all right, but only because Albert Einstein happened to be visiting Paris at the time and said, look, this isn't such a bad idea. Maybe it's even true.
Although Einstein championed the idea of wavy electrons, there was no experimental proof. In fact, quite the opposite. J.J. Thomson had got the Nobel Prize for proving it was a particle. But eventually, confirmation of the wavy nature of electrons did come.
The key experiments in the 1920s that proved that electrons are waves did so by firing electrons at the regular structure of a crystal, rather like the latticework structure we've got here. And those experiments showed the electrons bending round the atoms in the crystal, just as the waves here are bending round the structure of the pier. George Thomson in the 1920s was involved in experiments that showed electrons behaving as waves, doing just the things that ripples on a pond do, being diffracted, interfering with one another, all those kinds of things. And the story culminates because J.J. Thomson, the father, got the Nobel Prize for proving that electrons are particles, and George Thomson, the son, got the Nobel Prize for proving that electrons are waves. And they're both right. That's really the core of quantum physics summed up in that. Both of those Nobel Prizes were deserved.
It was the best of times and the worst of times for the physicists. They were in the middle of a revolution. They were struggling to come to terms with a problem that still troubles scientists now. Is the electron a particle or a wave? Or both?
If you asked, so to speak, if you asked light a wave-like question, lo and behold, it gave you a wave-like answer. But if you asked it a particle-like question, it gave you a particle-like answer. It conformed to what you asked it to do. In that sense, there wasn't a direct contradiction. There was obviously a very deep puzzle about how such behaviour was possible, but at least there wasn't a flat-on collision. It wasn't at the same time behaving like a bullet and like a spread-out flappy thing.
It's kind of like putting on two different sets of glasses and seeing the world in two different ways and being able to flip-flop back and forth between those two pictures. The general public doesn't have that ability, so they really see it as a very weird Alice in Wonderland world, and it disturbs them. Frankly, although I may seem very calm, it still disturbs me a bit too.
The disturbing nature of the electron confounded scientists in the 1920s. The Austrian Erwin Schrödinger set himself the task of writing down an equation that would predict how the wavy electron would behave. In 1926, he succeeded.
And in fact, it's a very simple equation. I could write it down on the back of an envelope with a great deal to spare. And here, in fact, it is. It simply has two terms in it. On one side of the equation is how things change with time. And on the other side of the equation, it says that's related to the energy of the system, which is the fundamental way of describing things in quantum mechanics. So there it is, a very simple equation. And the whole of atomic and subatomic physics, in some sense, flows from that equation. That shows you something of the wonderful power of mathematics to condense and crystallize out physical truth.
Although the behavior of the wavy electron could now be calculated, what no one could predict was that the wavy nature of matter was about to cause a major split between the quantum pioneers. If electrons were particles, it would be possible to know exactly where they were and how they would move around. Isaac Newton's laws of motion, written down in the 17th century, described precisely how particles of any size, from an apple to the moon, behaved. The certainty of Newton's world made the Industrial Revolution possible. The motion of anything could be predicted. The most intricate machines could be built. They ran as reliably as clockwork, just as Newton imagined the whole universe to work. It seemed unquestionable that nature was utterly predictable.
Newton's equations tell you exactly what's going to happen in the future. It turned out that the quantum world, the small-scale world, is different from that. It's unpicturable to us. It's cloudy in its character, And it's probabilistic, meaning that we can't say for certain what's going to happen. If this may happen, that may happen. We can say what the chances are, but that's as far as we can go.
The man who first realized the world runs on quantum chance was Werner Heisenberg. In 1927, he proposed the uncertainty principle. It states that because matter is spread out in space, wavy, it's impossible to say exactly where it is and what it might do next simultaneously.
This is absolutely real down in the depths of quantum physics. An electron itself does not know where it is and where it's going.
So we can never be certain about what's happening inside an atom. The effects are so small in our everyday world, we never see them. But the fact that at its heart nature is a game of chance meant scientists had to concede there was a real limit to what they could know with certainty. For many, this was unacceptable.
Several of the quantum pioneers didn't like what they'd invented. Max Planck wasn't really happy with it. Einstein wasn't happy with it. Schrödinger wasn't happy with it. And Einstein hated the idea that the outcomes of experiments could not be completely predictable. And in the famous expression, it's usually quoted, he said that I cannot believe that God plays dice with the universe.
And he thought that meant that the physical world had to be absolutely objective, had to be absolutely determinate and clear and certain. And of course quantum mechanics wasn't like that, and so he came to hate his grandchild.
From across Europe, the greatest minds of the age came together to settle the matter of uncertainty. The place was Solvay in Belgium. The year was 1927. The single photograph that remains of the conference shows a unique collection of scientific genius. Max Planck is next to Marie Curie. Behind Einstein are the other great doubters of uncertainty, like Prince Louis de Broglie, the original proposer of the wave theory. And on the top row, Erwin Schrödinger, whose equation made mathematical sense of wavy matter. Schrödinger and the others were not willing to take the leap into uncertainty with the young Turks Pauli and Heisenberg.
They've said, we've got to go with the new physics, that's the way the world is, you can't quarrel with that. And there's some quite sharp arguments and discussions between Einstein and Bohr on the one hand, and between people like de Broglie and a very sharp-tongued Swiss physicist Wolfgang Pauli, who essentially told de Broglie, I think, to shut up. He was being stupid. And de Broglie was a sensitive person and didn't like that, and he actually went away and did shut up. So it was a sort of turning point moment in which the young Turks won out over the old guard.
He couldn't believe that the outcome of an experiment depended on chance. And that's what led Einstein, for the last 20 years or more of his life, to fight this more or less lone battle against the theory that was taking physics by storm and try to find flaws in it. And he kept trying to invent experiments, thought experiments, imaginary experiments that would prove that quantum physics couldn't be true. And every time he did, people found ways round his thought experiments and found that they didn't prove that at all. And ultimately, perhaps just as well for him, after he'd died, people actually did some of these experiments for real, and every time they found quantum physics is right, probability rules.
By the late 1930s, quantum theory had found a new home, as European scientists sought sanctuary from Nazi oppression.
So there was this huge shift of science to America. You have this rich country and you have this ability to apply massive technology and money to fundamental problems.
But Americans, by and large, have taken quantum mechanics as a very useful tool and said, oh, don't bother me with all these philosophical arguments. I just want to be able to make calculations. And that's where our strength is, that we have taken this pragmatic viewpoint and ignored what are some troubling aspects. If we really sat down and thought about the philosophical meaning of what we were working with, we might not get anything done.
The company that had already made a fortune from knowing the electron was a particle were by now exploring the commercial potential of the wave theory of electrons.
Bell Laboratories began a research program in the 1930s to investigate possible solid-state physics alternatives to the vacuum tube.
Of course, we cannot build a calculating machine as flexible as the human brain. But even a man-made computer, designed to do hundreds of brain-like calculating jobs, might need an Empire State Building to house it and a Niagara Falls to power and cool it, if vacuum tubes were used in its construction.
Vacuum tubes were power hungry. Vacuum tubes gave off a lot of heat, which had to be handled. Vacuum tubes wore out and had to be replaced.
The goal was to replace the unreliable glass vacuum tubes with tiny solid devices that didn't need a vacuum to work. Scientists already had a good idea of how electrons moved inside a vacuum. They behaved like particles.
These aroused monkeys throwing pebbles at a target through a shutter ably portray what goes on in a vacuum tube.
But inside a solid, a crystal, the electrons behaved like waves, spreading out and bending around the atoms. To make electrons work in a solid, you need to know about quantum mechanics.
And because electrons are not only particles but also waves, and waves are spread out, then the electron wave sample the overall structure of the crystal, just as the particle-like aspect of electrons carries the unit of electric charge. So in a curious way, the particle-wave duality of electrons is essential, both aspects of it are essential for understanding how electrons behave in solids and therefore how electronics works.
In the early 1930s, solid materials were already being used in electrical circuits to detect radio waves. These solids were called semiconductors because they conduct just a little bit of electricity. Using quantum theory, for the first time, scientists could control the flow of electricity with precision. In the 1940s, this led to the development of semiconductor technology as a vital war weapon. Semiconductor radar could detect very small features like the conning tower of a submarine. It was this technology that Bell Labs used just after the war to create the modern era of electronics. The transistor was the semiconductor device that could amplify electrical signals, just like the vacuum tube, only better. The tiny transistor was the result of over 10 years' hard work at Bell Labs applying quantum theory to solve a practical problem.
The head of the department was William Shockley. The two key players in the transistor story, along with Shockley, are John Bardeen, a theoretical physicist, and Walter Brattain, an experimental physicist. On December 16th of 1947, they succeeded for the first time in amplifying an electrical signal with a solid-state device. A few days later, on December 23rd, they demonstrated their device to the department head Shockley and to a group of other Bell Lab scientists, and the transistor was born. But it was a lot of hard work, a lot of brilliance on the part of the scientists involved. It was not, oh, what are you going to do at the office today? Oh dear, I'm going to go to the office and invent a transistor. It's a lot harder than that.
The payoff was enormous.
Through their efforts, you may be able to get music with a flick of your wrist from the so-called Dick Tracy radio.
The miniaturization made possible by semiconductors laid the foundation for a new electronics industry. The first transistor took over 10 years to make. Today, 10,000 times more transistors than the population of the Earth are made every day. They're shrunk down to act as the pumps and valves that drive electrons around microchips. It all depends on quantum mechanics and the strange wave-particle nature of the electron. Over 100 years after its discovery, we can actually see what an electron might look like by using the computer technology it created.
One of the neatest pictures that sums up the quantum world is the one where a ring of atoms has been made as a little fence. You can see the waves of what used to be thought of as quantum particles sort of filling this quantum corral, as it's called. They can't escape. They're stuck inside there, and the waviness is kind of frozen there and can be photographed. That's something that the quantum pioneers would have loved to see.
Schrödinger would have said, way cool, dude.
Don Eigler at IBM has used a quantum microscope to make pictures of atomic surfaces. Each step in this picture of a surface is just one atom high. On top of the atoms, the wavy pattern is caused by a sea of electrons.
These are just electrons which are trapped in the surface layer, but within the surface layer they're free to move around. These electrons are waves. And the waves, when they move, they sometimes bang into features on our surface, like the step edges or the individual atoms which might be sticking out of the surface. And when a wave bangs into something, it reflects off of that thing. And when you have a reflected wave adding together with the incoming part of the wave, it sets up what we call a standing wave. These are regions where there are large oscillations which are fixed where they are in space, and regions where the oscillations go to zero.
I've always felt that the wave function was just a description of a reality. And the reality was deeper. It was a particle. And the wave function was just something mathematical up in a physicist's head. To actually see a physical wave function rippling across the surface is rather disturbing. If I was really honest, I'd probably have to tell you that I need to go back and reassess the way I've pictured the world.
Well, I'm probably somewhere in error, or maybe I'm just a heretic. I don't believe in this wave-particle duality mumbo-jumbo. I think it's mostly just the leftover baggage of having started off understanding the world in terms of particles and then being forced, because of the quantum revolution, to think of the world in terms of waves. And we're stuck with this dualistic way of looking at these very small particles. Don't even think about them as particles. Electrons are waves. And if you think of them in terms of waves, you will always end up with the right answer. Always.
The great debate on the nature of the electron and the meaning of the quantum world lingers on today. The success of quantum theory is unquestionable, but its meaning remains for each one of us to understand on our own terms.
People sometimes say that quantum mechanics shows that God plays dice. I don't think that's the right way of thinking about it. What I think we should say about it is that the universe is not God's puppet theatre. It isn't under tight divine control. It is allowed in some sense to be itself and to explore itself. And perhaps the openness of quantum theory, the unpredictability of quantum theory, is at the level of atoms and lower, an expression of an openness which I think is in the universe all over.
People have a kind of a deep religious need to know truth about the universe, to know how the universe works. That's why they're fascinated by black holes. And quantum mechanics is the most mysterious and exciting part of physics, and so it touches that chord. So it's not just the physics, it's this sort of mystic experience of knowing about ultimate truth. I think that's the appeal.
There's an easy way to get ahead overnight.